Okay, so the last thing we're going to be learning in this part of the lesson is finding roots or zeros of the polynomial function. So in other words, trying to solve an equation where we have a polynomial equal to 0. Okay, so we've already used the zero product property, and we know that if we have two factors multiplied together and that product equals 0, then we could just set each factor equal to 0 because one of them has to be 0. So we're going to use that same idea. In order to solve polynomials, we're going to factor them. Well, first of all, get them equal to 0, then factor them, and then set each factor equal to 0. The problem is, if you look at something like these two examples I have, we don't know how to factor these. The x cubed throws off our process that we learned for quadratics, and we could try grouping here, but it isn't going to line up in a way that it will be successful. So we need some help in how to go about trying to factor these. And that is where this thing called the factor theorem is going to come in. And what it tells us is if f of c equals 0, in other words, there's some number you know that when you plug it in to this function, you get 0, then that means x minus that number is a factor of that equation. So what that basically tells you, if you know a 0, then you know a factor, right? If this thing crosses the axis here at 3, 0, then x minus 3 is going to be a factor of that equation. When you factor it, x minus 3 will be one of those factors. Okay. And it does go the other way too. So if you knew that x minus 3 or c is a factor, then of course that factor could be set equal to 0, okay, and solved. So we're going to look at a couple of examples of this just to get this idea of the factor theorem down, and then we're going to talk about how to use it. So the first thing says, find a polynomial of degree 3, so we need an x times an x times an x, with the zeros -1, 1, -1, 0, and 4. Well, we just learned that if f of c equals 0, then x minus c is a factor of f. So if these are zeros, that means that f of each one of those is equal to 0, which means that x minus each one of these, minus -1, minus 0, and minus 4, each one of these is a factor. And so if we were going to write an equation for this polynomial, we could just start by multiplying those factors together. Now, of course, I don't need this -0. I could just write it as x, but I'm writing it that way so that you see the pattern. If it was not 0, then we would need to leave it there, right? So will this end up being a third degree polynomial? When I multiply x by x by x, that will give me 3, or x to the third. So this is a third degree polynomial, and each one of those will be at zeros. So we're good. So let's look at the next one. Use the factor theorem, which we've just been using, to find the zeros of this polynomial here. So we were given a x to the third plus 4x squared minus 4x minus 16. Given that x minus 2 is a factor, so they've given us a hint that we already know that this is a factor, which also tells you that x minus that 2 is a 0. That's what the factor theorem tells us, right? So what we're going to try to do is divide this factor out of this and then see if we can factor what's left to find the remaining zeros. So probably the best way to do that is to use synthetic division. It's going to be faster than long division. So I'm going to multiply and add and multiply and add and multiply and add. And if we know it's a factor, the remainder better be 0 because it's going to have to go in evenly. So that means that f of x is equal to this x minus 2 times, now I'm going to use these as my coefficients. Go down by 1, so 1x squared plus 6x plus 8. And this remaining thing is a quadratic. So we should be able to factor that. Two numbers that multiply to give you 8, but add to give you 6. And then if we were going to set this equal to 0 to find all the zeros, then I have x minus 2 is 0, x plus 4 is 0, and x plus 2 is 0. So these would be my 3 zeros of the function. So the factor theorem is very helpful because if we already know something that's a factor, we can divide it out and then get down to a lowered powered polynomial that we probably, hopefully, do know how to factor. So that's kind of the goal in using it, is if we could just get 1 0 to factor out, then usually we're left with something that's more manageable. But how do we know? I mean, this one just told us, yeah, hey, this is a factor. How do we know if we're not told that, what we should even try? And that's where this last theorem comes in, the rational zero theorem. And what it basically does is it gives us the possible numbers that could be zeros. Well, at least rational zeros. Rational zeros are numbers that we can write as fractions, so it does include whole numbers. Right? So it's giving us a list of possible whole numbers and fractions that could be zeros of a polynomial. And so we basically then, once we have that list, we need to just try to figure out which one works, which one actually gives us 0. And the best way to do that is to use synthetic division and see if your remainder is 0. If your remainder is 0, then that tells us that that factor goes in without a remainder. So we can work on then factoring. It is a 0, and we can work on factoring it more. So let's go, oops, did not want to skip the whole page. Let's go to this theorem and look at what the list of possible numbers to try is, where that comes from, and then we'll practice using it. So it's a little weird. The RZT, rational zeros theorem, tells us the possible zeros are all the factors of A0. A0 in my polynomial is the constant. The constant, the one without any x's. And we're going to divide that by all the possible factors of an. An is the leading coefficient. So what we're basically going to do is we're going to list all the possible factors of the constant and all the possible factors of the leading coefficient, and then create a list of all the possible combinations of those two lists on top of each other. So let's try it. Example 1. Here is my function, f of x equals 2x cubed plus 7x squared plus 2x minus 8, and I'm going to list all the possible rational zeros. So the constant, which is on top, would have 1, 2, 4, and 8. These are the factors of my constant. My constant is -8, right? So what goes into 8? 1 and 8, 2 and 4. And my factors of the leading coefficient is just 2, so that'd be 1 and 2. So my possible roots, I need to take every number from this list and put it over every number from this list. So I would have 1 over 1, which is 1. I'd have 1 over 2, which is 1/2. Then I'm going to go to the next one. I'd have 2 over 1, which is 2. Whoops. And then I'd have 2 over 2, which is 1. I've already listed that, so I'm not going to list it again. Then we'd go to the next one. 4 over 1, that would give me 4. 4 over 2, that would give me 2. I already have 2 there, so I'll just add the 4. And then I have 8 over 1 and 8 over 2. And the only new one there would be the 8 over 1. So now I have a list of possible numbers. If there is a 0 of this function that can be written as a fraction or a whole number, it's in, I did not mean to do that. It's in this group of numbers. If I could get that group of numbers to show up properly. Okay. So that was our answer to part A. Now in part B, it says find all of the rational zeros. So now I have to do some work. I need to try to see if I can get one of these numbers to divide in evenly. You could, let me go back to my problem. Of course, it's on the other page. You could, if you really wanted to, come on now. Take this number, plug it into this function, see if you get 0. Take the opposite of it, plug it in, see if you get 0. But that's a little bit more work than using synthetic division. So we're going to try using synthetic division. So what I'm going to do is I'll take my first, we had 1, right, and -1. So I'm going to start with 1. I'll list my coefficients. I have them from the other page. It's 2, 7, -2, and -8. I'll bring down my first coefficient, and then I'm going to multiply and add and multiply and add. And I can see right away that this is not going to turn out to be 0. That's the golden ticket we're looking for. If it divides in evenly, its remainder is 0. So 1 isn't it. Oops, that was supposed to be the eraser. So why don't I try -1? This is a lot faster in terms of arithmetic. Still not going to get it done than actually plugging it in. It still sometimes takes a little time to find one of these. Now, personally, I'm going to skip the, I know the next one on my list is a fraction, but just like you, I'm going to try to avoid the fraction. So I will try the next whole number. Oh, this doesn't look promising. Now that's not going to end up being 0. So let me try the negative version of that. Okay, so I'm just going through my list methodically. I did skip the fraction. I'm going to try it at the end if I have to. So let's see, -4, -6. Did I just write that down wrong? I think I did. You know what I just realized? I didn't double check my coefficients. It's a +2. It's 2, 7, 2, -8. Yeah. Bummer. I know better than that. See, I just did that. I'm going to try to go faster. And then that's not working smarter. It's working harder. Made my life harder. Okay, so I should have done that with my 1 and my 2 and my 1 and my -1 and my 2, but guess what I know? I know this one's going to work. That's how I noticed my mistake. So I would have had the same it didn't work result, whether I had written the coefficient correctly or not. But this time, now that I have them correct, I'm going to multiply, I'm going to add, I'm going to multiply, I'm going to add, I'm going to multiply, and there it is. Okay. So let's say I was on a test or a quiz and I was trying to do this process. This is where my scratch paper comes in. I'm going to take my scratch paper and I'm going to do my synthetic division there till I find the one that works. And then I would transfer the one that works onto my paper. So I could now write, okay, here's my function. It's x minus -2, so x plus 2, times 2x squared plus 3x minus 4, okay, equals 0. So now I found actually, you know what? We're going to get rid of this word too. I'm just going to say find all the zeros. So I want to solve the whole equation, not just the rational ones, okay? So I have my list of all the possible ones. I've gotten this down to x plus 2. So I know that my zeros, if I'm going to just give myself a place to write the answer, the first one's going to be -2. And then I'm not sure what else there might be. I now need to work on solving this equation. 2x squared plus 3x minus 4 equals 0. So take a minute to look at that. You can either factor it. That's where I would start. I would try to factor it. Or, of course, you could apply the formula. Now, if I try to factor it, I'm going to use my AC method. And I'm looking at possible combinations of things that multiply to -8 and add to 3. I don't have one. Even if I change the positive and negative here, this is not going to factor. So I'm stuck with x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Simplify under the square root first. That'd be 9 plus 32, which is 41. And I don't think I can simplify the square root of 41. 4 doesn't go into it, 9 doesn't go into it, 16 doesn't go into it, 25. So this is about as good as it's going to get. So I will add that to my list. And now I have all of the zeros. I have the rational 0 here. And these are irrational. The reason you know that is because there's a square root left in them. If anytime you have a square root of a number that's not going to give you a nice, even, perfect whole number, it's called it'll be an irrational number. So we did it. We found all of the zeros. Okay, there are 2 more problems similar to this. I do want you to give these a try and see if you can do the same thing, finding all the roots. Let me start you off by making our list of possible roots, right? So remember, you take the possible factors of your constant and you divide them by the possible factors of your coefficient, your leading coefficient. Well, in this case, your leading coefficient is just 1. So your list of possible roots is just going to be those factors of the constant. So that's nice. One thing I also want to warn you about on this one is if you're testing, whatever you put here, when you line up your coefficients, do you notice something? It goes from x cubed to x. So a coefficient of x cubed, a coefficient of x squared, a coefficient of x, and the constant. Here is the first time we've needed a placeholder, and you have to have it or the whole thing will get screwed up. So I want you to work on that one. And then before you hit pause, I just want to also fill in the possible roots for this one here. I'm looking at the same set for the 4, but now I also have a 3. So I'm going to have 1, 1/3, 2, 2/3, 4, and 4/3. So I got a lot of fractions in that list. Doesn't look like I'm going to need a placeholder for that one because it goes from 4 to 3. Oh, yes, I am. I am going to need a placeholder. It goes from 4 to 3 to 1. So same thing. When I set this up, I'll need 3, -11, 0, 10, -4. Okay. Now you're in good shape. go ahead and press pause. You might have luck on picking the winning route, the winning possible route early, or you might be unlucky and end up doing 10 synthetic division problems before you find it. But keep trying and then keep factoring and see if you can find all the roots. All right. If you gave those a try, you might have experienced the same thing I did, that one of those was a lot easier than the other. Number 2 wasn't so bad. I did a little bit of trial and error, and I got that -2 is going to be a 0. It divided out with a 0 remainder. So that means that this polynomial equals x minus -2, or x plus 2, times x squared minus 2x plus 2. How come I have a -2 there? Hold on just a sec. Nope, I didn't do it wrong. I just wrote it wrong there. So I think I'm okay. All right. 1x squared minus 2x plus 2 here. Yes. Now, so I already know that the solution to this one is the -2. I have that listed here. So now I'm trying to solve just the x squared minus 2x plus 2 equals 0. It does not factor. There are not two numbers that multiply to give me 2, but add to give me -2. So I apply my quadratic formula. This is where I had the minus, but then I actually had done the subtraction correctly. So 4 minus 8 is -4. So I'm going to be, now I have a complex solution. The square root of -4 is plus or minus 2i. And I did factor the 2 out of the top and cancel it with the 2 in the bottom. So I have two complex zeros for this particular polynomial, 1 plus I and 1 minus I. So my remaining zeros. So keep in mind, if we were like graphing this, these would not be graphable. That means these are not x-intercepts, only this one would be. Okay. Last but not least, we had this long one. Lots of possible fraction roots. I felt like, oh, this is going to be easier because I got -1 to work. And so then I tried to rewrite this factoring, right? So that I had x minus -1 and then 3. Oh, but I've got to start with x cubed since this is an x to the 4th. And I don't know how to factor this. So I'm basically left at trying to do this process again. I'm now trying to find a 0 of this that I can factor out. I didn't necessarily make a new list, which I could have. I could have done a new possible roots list for this with the factors of 1, 2, 3, and 4. Oh, wait, it's exactly the same list as what we already had. This list and this list, 4 and 3, 4 and 3. That's why I didn't do it, because I can basically just look at my original list. But now when I'm plugging things in, I'm plugging them into here to try to see if they make this a 0 so that I can factor this further. So I did some trial and error and it took a while, but I finally found one that worked and it was a fraction. So using these coefficients, bringing the 3 down. The nice thing is when you multiply the 3 by the 2/3, the 3's cancel. And when you multiply the -12 by the 2/3, it does come out to be a whole number. So that part isn't awful. So now, once I found this, I know that x plus 1 is still a factor. And then for this guy, x minus 2/3 is a factor. So there's my first two zeros, -1 and positive 2/3. And then here are my coefficients, 3x squared minus 12x plus 6. So this is what I am now trying to solve. 3x squared minus 12x plus 6 equals 0. I factored the 3 out because that's going to make life a little easier, but it still doesn't factor. Wow, we have a lot of doesn't factors in this set of examples. So I once again applied the quadratic formula and simplified my answer to get my final two roots. They are irrational, but they are real. So they would in fact be x-intercepts. Whew, that was a tough one.